I'll start. So, hello, I'm Brigrishi Mishra, research scholar at IIT Bombay, and this is the fifth online session of Elements of Solar Energy Conversion. So, in this week, mainly shadings and estimation of radiation on tilted surface. These two things were covered. So the shading portion will be taken care by the another TA, Mr. Pawan, whose online session is on tomorrow, 6 to 7 p.m. And in this lecture, I'll cover these topics: the estimation of radiation on tilted surface, what is the view factor, how to calculate it, and the radiation augmentation. So. So for a tilted surface, there are for each radiation consists of two type of radiation: uh, beam radiation. So beam radiation as well as diffuse radiation. Okay, and we want to calculate it on a tilted surface whose tilt angle is beta. So suppose I draw a sky dome like this, and so this is the diffuse sky area, you can call it AS. Okay, and this is the normal. So suppose I have a collector here, and suppose this is the direction of beam radiation, and my and this portion is the circumsolar, and this is the horizontal portion, horizontal area. So beam radiation we can calculate very easily. Now diffuse radiation has these three parts. One portion is whatever it diffused to the sky, another one is around circumsolar, okay, and the third one is from the horizontal reflection, whatever it get from the horizontal. Okay, so simply I can write here T is the tilted radiation on a tilted surface. So IT is nothing but IT comma B plus IT comma D comma ISO. Here ISO means isotropic, that means in this area diffuse sky, and T again tilted, and D means diffuse, plus ITD circum, I can CS, and the last one is from horizontal, ITD HJ. Now there are some other radiation that tilted surface gets from the reflection of radiation from surrounding objects. So, or you can say the simply the neighboring objects, whatever you can say. So this is IT reflection. Okay, so in terms of horizontal radiation can be further simplified in terms, since we can measure radiation on a horizontal surface by using pyranometer or pyrheliometer. Okay, so in terms of horizontal beam and diffuse, beam and diffuse radiation, IT is IBRB plus ID ISO FCS plus IDCS into RB plus ID comma HZ FCHZ plus I rho G FCG. Okay, so this RB relates the horizontal beam radiation to the tilted surface beam radiation. So RB is nothing but IT by I is the total radiation on the horizontal surface and IT is on the tilted surface. So it can be written as like ION cos theta T by ION cos theta Z. So it is nothing but simply cos theta T by cos theta Z. Okay, and similarly, so what are these things? FCZ, so FCS, FCHZ and FCG, these are called the view factor. Okay, here C means collector, S sky, HZ means horizontal area and G means ground. Okay, so so the first question is derive expression for view factor from collector to sky, that is FCS, and from collector to ground, that is FCG. These two angles we will derive, which will complete this expression. So okay, so suppose the tilted angle, the collector's tilted angle is beta. Okay, so first we should know what is view factor. Okay, so for the view factor, suppose I have two surfaces like this. Okay, this is A1 and this is A2. So I can connect these two surfaces like this. So you can name it this C, D, E, F. I can also connect the diagonals. So CF is one diagonal and D is another diagonal. Okay, so in terms of view factor, so for example view factor from A1 to A2 donated as F12, so it is nothing but diffuse energy leaving A1 directly towards and intercepted by A2, means whatever the A2 collecting the diffuse energy leaving from A1 divided by total diffuse energy leaving A1. Okay, so for any view factor or for any surface, okay, view factor is 0 less or equals to F12 less or equals to 1. So it value ranges from 0 to 1. It cannot be negative and it cannot be greater than 1. Okay, also from reciprocity theorem, the area of collector A1 into view factor from 1 to 2 equals to area of collector A2 into view angle from 2 to view factor from 2 to 1. So this is the reciprocity theorem. Okay, now so for any surface, okay, for any surface means, for example, for this A1, the total if we consider all the neighboring objects who are intercepting the energy diffused by surface A1. So from law of energy conservation, summation of all such surfaces, okay, so V factor from 1 to all such surfaces equals to 1. Okay, so here in this case we are considering only two surfaces, A1 and A2. So it was also discussed during lecture videos, Hotel's crossed string rule. So you can search in Google what it is. We will simply use the relation derived by Hotel. Okay, so from Hotel's crossed string rule, V factor from A1 to A2 is so A1 to A2, so F12 is, so the sum of the two diagonals, that is CF plus D minus the distance between A1 and A2 in both the corners, that is minus CE minus DF divided by 2 times the height of the A1, and similarly we can also derive F21. Okay, so now we will so this is the general idea of view factor. Now we need to derive from collector to sky and from collector to ground view factor. So first we'll consider collector to ground. Okay, so for example, this is the collector I have, okay, and this is the ground. So I can consider this is the collector, I can take as a C and D, and I can take ground like this. Okay, and this ground point is F and this is E. So here D and F are very close, that means we can say both are coinciding. Okay, and this collector is making an angle with the ground beta. This is a tilt angle. So this is collector and this is ground, and the assumption is these collector and ground have infinite length. Okay, for the this view factor we can calculate only by considering that collector and ground has infinite length, or infinite in length. So assumption collector C and ground G are infinite in length. Now if I connect this CE, okay, so from this formula, collector to ground view factor FCG is CF plus D. These are the two diagonals. Okay, so here in this case it is so you can say there are two terms CD and DF. So if you consider the same way here, so the cross section CF and D, so in this case what will be the expression? Okay, so here simply D plus C minus, sorry, not CE, it is CF. Okay, so DE will be one diagonal and CF will be another diagonal. Okay, and now the distance minus CE minus DF upon height of the collector into 2 times, so 2 times CD. Okay, now since we have considered here that D and F are coincide, so DF will be 0. Okay, and also since D and F are coinciding, so CF equals to CD. So I can modify it like FCG is D plus CD minus C divided by 2 times CD, or I can also modify it CD. I can write it like this: CD plus D minus C by 2 times CD. Okay, now we have to calculate this D minus C. Okay, so D minus C means this is the D portion, so D minus C. So what I can do is I can draw perpendicular from C to the horizontal and name it as G. So this is 90 degree. So see this triangle CGF, we can calculate easily that the projection of CD on the ground DG is nothing but, so DG is CD into cos theta. Okay, now since we have assumed that collector and ground are infinite in length, so so that means this angle, okay, kept on increasing, and at infinite length it is 0 degree. So that means, or I can, in a simple language, I can say that when CF and FE, or simply D, at infinite length, then C will be equal to ED plus DG. That means this distance, okay, this CE distance will be equal to this EG distance, okay, when CD and FE are at infinite length. Okay, so that means assuming CD and D of infinite length, I can write that CE is nothing but equal to EG, and now EG is what? DE plus DG. So this is DE plus DG. Okay, and we have already calculated here DG equals to CD cos theta, so I can write here C equals to DE plus CD cos theta. So this will give us D minus C equals to CD cos theta. Now putting this value here, we can get FCG equals to CD, sorry, this is minus, okay, so CD minus CD, sorry, this is not theta, since we have assumed tilted angle beta, it is beta. So cos beta, cos beta, cos beta. So CD minus CD cos beta by 2 CD. So CD will get cancelled, and thus you'll get FCG equals to 1 minus cos beta by 2. Now what will be view factor? We need to calculate view factor from collector to sky also. So for this collector, there are only two surfaces who are accepting the radiation we are considering in this case, that is one is ground and other one is sky. So the summation of both the view factors should be equal to 1, that is FCG plus FCS equals to 1. And since we have already calculated FCG, so FCS, and in case of sky it is nothing but this beta and the whole sky is the view factor. Okay, so FCS will be 1 minus FCG, and this is nothing but 1 minus cos beta by 2, and if you solve it you will get FCS equals to 1 plus cos beta by 2. So this is the view factor from collector to sky. Okay, so in this way we have derived the formula for view factor from collector to ground as well as view factor from collector to sky, which is nothing but 1 minus cos beta by 2 and 1 plus cos beta by 2. So any question here? Okay, if not, I'll move to another problem. So in this problem I have considered the radiation augmented from a reflector, or I can say simply the case where one reflector is placed on the horizontal surface to augment or to enhance the radiation received by the collector. That means in a simple case I can say that suppose I have a collector like this, suppose I have this collector. Okay, this is collector C, and now I have put reflector on the ground, so that whatever the radiation reflected by this reflector will be focused on the collector, and thus collector will get more radiation. So this is reflector R. Okay, now suppose the collector length is N, reflector length is P, and collector reflector both have the same width M, and the angle between reflector and collector is psi. Okay, so in that case the total radiation received by the collector, okay, is nothing but IBRB plus ID FCS plus IR rho R FCR plus I rho G FCG. So this term, this extra term is from the reflector. Okay, IR rho R FCR. Here IR is the radiation reflector getting, okay, and rho R is the reflectivity of the reflector, and FCR is the view factor from collector to reflector. So here we have 3 view factors, so FCS plus FCR plus FCG equals to 1. Okay, so now the question is, a vertical window receiver in a passive heating system is 3 meter high and 6 meter long. Okay, so 3 meter high means N equals to 3 and M equals to 6. Okay, and there is deployed in front of it a horizontal diffuse reflector, which is this, of the same length, that means 6 meter, extending out 2.4 meter. So P is 2.4 meter. Consider window as a collector. So here we will consider window as a collector, which is collecting heat from the reflector. What is the view factor from the reflector to the window? That means FRC. View factor from window to reflector, FCR. And view factor from window to the ground, that is FCG. Okay, so we need to calculate FCR, FCG. Okay, I think here I missed one thing, the tilted angle. Okay, I think I missed one thing here. Okay, no, that's fine. Yeah, so the angle between collector and reflector, since it is a window, so window is a horizontal, okay, and window is a vertical and reflector is a horizontal. So the angle, so the tilt angle of collector is 90 degree. So these three quantities, these four FRC, these four quantities I need to calculate, and the tilt angle is 90 degree. Okay, so again so first we can calculate FCS. So FCS is nothing but 1 plus cos beta by 2, and here beta is 90 degree, so cos 90 is 0, so it is simply half, which is 0.5. okay, so FCS is 0.5. now we need to calculate FCR. okay, so FCR, so for this we can calculate that, like in the lecture it was shown that there is a chart to calculate FRC. okay, chart to calculate FRC, that means the view factor from reflector to the ground. okay, but here we don't want to use chart. We can assume that these surfaces C and R are very long in extent, so that we can apply this this Hotel's cross string rule. okay, so so assuming, so if surfaces C and R, means window and reflector, are very long in extent, that is M is large relative to N and P. Although here M is 6, N is 3 and P is 2.4, it is not significantly large, but we can assume this assumption here. Otherwise we have to use chart to calculate the FRC. okay, so FRC will be N plus P minus S by 2 pi P. And what is this S? So this is N, this is P, and this is S. okay, so here S can be calculated as, this is not exactly the like right angle triangle, I draw it like this. okay, so S can be calculated as N square plus P square minus 2NP cos psi. okay, and now psi is 90 degree in this case also, because psi is the angle between collector and reflector. So in this case psi is also 90 degree, so cos 90 0 again. So S will be N square plus P square to the power half, and if you put the values you will get as around 3.84 meter. okay, so FRC is N plus P minus S by 2p, and by putting the values n equals to 3, p 2.4, and as we calculated here 3.84 by 2 times 2.4, you'll get 0.33. okay, so this FRC is 0.33. now we need to calculate FCR. okay, so for the FCR we can use the reciprocity theorem. okay, so using first we can calculate the area of collector, which is nothing but 3 into 6, that means 18 meters square, and area of reflector is 2.4 into 6, that means 14.4 meters square. So using reciprocity theorem, can say that area of collector, that means 18 into view factor from collector to reflector, FCR, equals to area of reflector into view factor from reflector to collector. And we have calculated FRC here 0.33. so FCR is 14.4 by 18 into FRC. So this value is around 0.264. okay, now I have FCR here and I have already calculated FCS here. okay, I can calculate FCG, and the sum of these three is equals to 1. so I can use different color. so FCG equals to 1 minus FCR plus FCS, and it is 0.264.5. so FCG is 0.236. okay, and this way we can calculate the view factor for all, from collector to ground, collector to sky, collector to reflector, and reflector to collector. okay, what you can do is you can use the chart given in the book to calculate the FRC. okay, and then calculate this FCR and FCG again and see the difference. okay, I don't think there will be a large difference, because anyway we can assume this assumption that surfaces C and R are very long in extent. okay, so any question here? okay, so now I will move to the last question of this session. so here we'll use the isotropic model to estimate the beam, diffuse and general reflected components of solar radiation and the total radiation on a surface sloped 45 degree toward the south at a latitude of 40 degree north for the hour 2 to 3 p.m. on February 20. and here total radiation on the surface is given as 1.04 megajoule per meter square and ground reflectance 0.6. okay, so isotropic model. So isotropic model considers that there is no circumsolar or horizontal brightening radiation part, diffuse radiation part is involved in the calculation of diffuse radiation, and for most of the cases it is very true. okay, so yeah, for isotropic model, IT is IBRB plus ID 1 plus cos beta by 2 plus I rho g 1 minus cos beta by 2. So this is the beam radiation, this is diffuse, and this is the radiation on the ground. Okay, which is here given the total radiation 1.04 megajoule total radiation. Okay, so what are the things here we have given? So first is February 20. So Feb 20 means n equals to 31 plus 20, which is 51. Okay, so n is equals to 51, and we have given that this surface is sloped to 45 degree. That means tilt angle beta is 45 degree and sloped 45 degree toward the south. So toward the south means the surface azimuthal angle AZ is 0 degree. Okay, so surface azimuth angle 0 degree reduces the complexity of the problem. So here the question says AZ is equal to 0 degree, and the latitude of the position is given 40 degree north. So L is 40 degree north. Okay, so since this is the problem of radiation, we need to calculate the declination angle, okay, as well as our angle to calculate the beam radiation and other tilted angle for that surface. Okay, so first calculate the declination angle delta. It is 23.45 sine 360 by 365 284 plus n, and n we have already got 51, so I have already calculated the angle. So this is minus 11.6 degree. Okay, so delta we got. Now we need to calculate the omega. Okay, so it is given from 2 p.m. to 3 p.m. So we can calculate omega at 2 p.m. as well as at 3 p.m. So omega at 2 p.m. naming it omega 1. So this is so standard time minus 12 into 15, this is the formula. So standard time in hours, so it is 2 p.m. so 12 plus 2 14 hours. So 14 minus 12 into 15, this is 30 degree. And similarly omega at 3 p.m. omega 2 equals to again st. So for 3 p.m. it is 15 minus 12 into 15, so this is 45 degree. Okay, now we need to calculate the hourly extraterrestrial radiation between this omega 1 and omega 2. So hourly extraterrestrial radiation, okay, which is I naught equals to ISC 1 plus 0.033 cos 360n by 365 into cos theta z, and cos theta z is cos L cos delta cos omega plus sin delta sin L. Okay, and now we have to integrate this equation from omega 1 to omega 2 to get the average radiation between 2 to 3 p.m. Okay, the extraterrestrial radiation, of course. So for a period of omega 1 to omega 2 I naught. So after integrating, I'm writing the integration here. This we have already covered in previous lecture, I guess, in the online session of third online session. So you can check that video again to just brush up your memories. So here I'll directly write the formula. So I naught will be 12 into 3600 by pi into ISC 1 plus 0.033 cos 360 n by 365 into cos L cos delta. Now the integration of this cos omega will be sin omega and limit omega 1 to omega 2, so it will give sin omega 2 minus sin omega 1, and this term there is no omega, so simply integration of d omega, which is nothing but omega 2 minus omega 1, but since omega are in the degree, we need to convert it in the radians. So it is pi into omega t minus omega 1 by 180 degree sin L sin delta. Okay, now we know all the values. I forgot to put here. So ISC is 1367. Okay, so I naught is 12 into 3600 by pi. ISC is 1367. Okay, and also putting the other values, cos 360 into 51 by 365. Here cos L is given, that is cos 40 degree, delta is minus 11.6, sin 45 minus sin 30 degree plus pi into 45 minus 30 by 180 sin 40 degree sin minus 11.6 degree. So if we calculate this, the extraterrestrial radiation for 2 to 3 pm will be 5.807 megajoule per meter square. Okay, now since I have this extraterrestrial radiation, and I also know the total radiation coming to the surface, which is given as 1.04 megajoule per meter square. So I can calculate the clearness index, which is an important quantity to calculate the diffuse radiation. Okay, so clearness index KT is I by I naught, which is 1.045 by 5.807, and it is 0.18. Okay, now we need to calculate the hourly diffuse radiation ID. So if you remember the lecture, so there was a relation to calculate hourly diffuse radiation given as RD equals to ID by HD. Here this HD is the monthly average diffuse radiation, RD is the diffuse factor, and ID. So if you know these, and there are expressions for RD which involve the hour angle, sunrise sunset angle, you can check the previous lectures. Okay, but apart from it, I am using a simple relation. Okay, so in the question itself it was given that you can use the Orgel and Holland's relation for ID by I to calculate the diffuse radiation, hourly diffuse radiation. So what it is, ID by I is 1.0 minus 0.249 into kT, and this is for kT less than 0.35. So this formula very well like agree with this calculation. So it is given in several books. You can just search this Orgel and Holland's relation, and you will find this kind of relation. So there are different relations for different values of kT. Okay, so since our kT is here 0.18, so I am using this formula. So from this you can calculate ID is 1.0 minus 0.249 into 0.18 into I, and which is 0.9936 megajoule per meter square. So we can, since we got to know the diffuse radiation, we can calculate the beam radiation. So IB is nothing but I minus ID, so 1.04 minus 0.9936, and it is 0.0468 megajoule per meter square. So you can check for this 2 to 3 pm here the IB is very low compared to ID. Okay, and we can sense this also from here that the extraterrestrial radiation is 5.807, and the radiation we are getting on Earth is 1.04. that means more than 5 times lesser compared to extraterrestrial radiation. Okay, so yeah, we got IB, ID here. These values are on the ground surface. Okay, so now from the isotropic sky model we have already written there. I'm writing it again. IT equals to IB RB plus ID 1 plus cos beta by 2 plus I into rho g 1 minus cos beta by 2. Now we need to calculate RB. Okay, RB is cos theta t by cos theta z, which is now this is for tilted angle, so we will replace L with L minus beta. So this is for the cos theta. Okay, so we will replace L with the L minus beta for the expression of cos theta. So it is cos delta cos omega cos L minus beta plus sin delta sin L minus beta, and divided by cos L cos delta cos omega plus sin L into sin delta. Now we have all the values L, delta, omega, beta, but what about omega? So this omega we can, since the time is given from 2 pm to 3 pm, we need to calculate omega for the middle value, that means for 2:30 pm. Okay, so omega for 2:30 pm is 14.5 minus 12 into 15, which is 2.5 into 15, and it turns out 37.5 degree. Okay, so now we know the omega, and the beta is given at 45 degree. Okay, L is 40 degree, delta is minus 11.6 degree. So putting all these values, cos minus 11.6, cos omega is 37.5 cos L minus beta, that means 40 minus 45 plus sine delta 11.6, and sine L minus beta again 40 minus 45 upon. Now here for the bottom we don't need to replace L with L minus beta, since we are calculating it for the horizontal, that means for the zenith cos theta z. So it is simply cos 40 cos minus 11.6 cos omega 37.5 plus sine 40 and sine minus 11.6. So if you calculate RB, it comes around 1.7. okay, so we can calculate total radiation on tilted surface IT as IB 0.0468 into RB 1.7 plus ID 0.9936 into 1 plus cos beta, and here beta is 45 degrees, so cos 45 degree by 2, and I, this portion I rho g into 1 minus cos beta, and rho g is given in the question, ground reflectance 0.6, this is rho g. okay, so plus 1.04, here I into rho g, I means total radiation on the horizontal surface, so 1.04 into ground reflectance 0.6 into 1 minus cos 45 by 2. So the radiation on tilted surface is 1.0186 megajoule per meter square, and if you compare it with the horizontal radiation 1.04. okay, so of course the radiation on the horizontal surface is greater compared to the radiation on the tilted surface in this case, but it is not significantly greater. okay, the ratio is very low. So if you calculate IT by I 1.0186 by 1.04, so the ratio is 1.0186 divided by 1.04, so it is around 0.979, or I can say 98%. okay, so only 2% loss. So and 98% of the horizontal beam radiation is received by the tilted surface collector. okay, so this way we can calculate the beam radiation on the tilted surface. So yeah, that's it for today's session. If you have any question, please ask. So in this we have seen the what is view factor. We have derived the relationship for of view factor for collector to sky as well as collector to ground, FCS and FCG, and we have also solved a question where the reflector is used to augment the radiation received by the collector. We have calculated the view factor of so here we have calculated the view factor of collector to ground, collector to reflector, reflector to collector, and in the last question we have used the isotropic model to estimate the beam, diffuse and general reflected components of solar radiation and the total radiation. okay, sorry, it is beam, diffuse and general. So this portion will give you the beam, this portion will give you the diffuse, okay, and this portion will give you the general reflected part. So we have calculated this, and we have also seen that the almost 98% of the of the radiation tilted surface is getting compared to the horizontal beam radiation for 2 to 3 p.m. on 20th February at a latitude of 40 degree. Okay, so if there is no question, I'll close this session. So we will meet on next session.